Hello, everyone. Once again, thank you so much for your time. Today, I'd like to continue on our discussion on EMC consideration. Our topic for today's discussion is also a conclusion on shielding effectiveness. There are two series, A and B series. This video is the B series. So please take a look on the A series before you come to this video, because this is a continued video from the A series. Shielding effectiveness fall on three factors: 1, absorption; 2, reflection; and 3, multiple reflection. This will be the part 28 series discussion. The earlier on series discussion on EMC, I have put the video link under the description. So please look at the video if you're keen to know more about EMC. This is my email. If you have any question regards on today's discussion, please drop me an email. Before I continue, I'd like to urge you guys to support this channel by pressing the like and subscribe button. I need your help, guys. Thank you so much. Earlier on, we have mentioned about far field. So now we're going to concentrate on electric field and also magnetic field. When your source of disturbance is actually electric field, okay, the total loss for an electric field is obtained by combining the absorption and reflection loss. The multiple reflection correction factor B is normally neglected in the case of an electric field. Since the reflection loss is so great and the correction term is small, okay, at low frequency, reflection loss is the primary shielding mechanism for electric field. At high frequency, absorption loss is the primary shielding mechanism. From here, okay, we conclude that electric field is almost the same as far field. Let's take a closer look on magnetic field. The total loss for a magnetic field is obtained by combining the absorption loss and the reflection loss. If the shield is thick, when absorption loss exceeds 10 dB, the multiple reflection correction factor B can be neglected, else the correction factor B must be included. Let's take a look on this diagram on your right. This diagram is frequency versus shielding effectiveness. Okay, you can see that the source is based on electric field, far field, and magnetic field. From here, we can conclude that if the source is electric field, then you can have an easier task to shield it, because you can see from here, when the disturbance noise is from electric field, you actually can have a form of shielding effectiveness, okay, which means that this problem you can resolve much easier. Okay, when your source is considered under far field, okay, not so bad, your shielding effectiveness is also at least 130 dB. Okay, most likely you will be able to shield against far field. However, when your source of interference is dominated by magnetic field, then you have some concern. Worse, if the magnetic field is at low frequency, you can see that at low frequency for magnetic field, you don't actually provide much shielding effectiveness. In fact, you will have a bigger problem if the magnetic field occur at low frequency. On the next slide, I'm going to explain to you how we can resolve magnetic field at low frequency. Okay, but from here you can see that if your disturbance source is magnetic field, then you need to spend more time how to shield it properly as compared to electric and far field. Because the characteristics impedance of a conductor increase with frequency, okay, the reflective loss decrease with frequency. The absorption loss, on the other hand, increased with frequency because the skin depth decreased with frequency. Thus, the characteristic shape of the shielding effectiveness with absorption loss dominate at high frequency and reflection loss dominate at low frequency. So this is what we have studied earlier on. The reflection loss to a low frequency magnetic field is small. Okay, you can see from the earlier on, you don't have much reflection loss under magnetic field. Due to multiple reflection, this effect is even more difficult in a thin shield. The primary loss for magnetic field is absorption loss. Since both the absorption and reflection loss are small at low frequency, the total shielding effectiveness is low. It is therefore difficult to shield low frequency magnetic field. Additional protection against low frequency magnetic field can be achieved only by providing a low reluctant magnetic shunt path to divert the field around the circuit being protected. Okay, let's take a look on this diagram. Okay, for example, this part is your sensitive device or component. Okay, and magnetic field is actually moving from the left to the right. So what you can do is basically you provide this low reluctant magnetic shunt path here. So when the magnetic propagate, okay, it will actually take this route, the low reluctant magnetic shunt path. And with this, you actually re-divert the magnetic field. So instead of disturb your sensitive component, okay, the magnetic field actually travel around it, and this successfully design a shielding effectiveness against magnetic field. With this, I'd like to end my discussion. Please like and subscribe. Thank you so much.